Welcome to Brain Vision.
In this problem, we're going to be looking at the Earth and some distant galaxy over here. And light from this galaxy is emitted with a wavelength of 434.1 nanometers. And it travels across space, this great distance, and by the time it reaches the Earth, it has a slightly different wavelength. Now it's 438.6 nanometers. So let's call this our initial wavelength. I'll call that lambda initial. And over here is lambda final. And what's we see is that lambda final is greater than lambda initial. What's happening is that the wavelength got bigger. So I like to think of it a little bit like a spring. It's not a perfect analogy, but if you imagine you have this spring and it starts off looking a little bit like that, then it gets stretched out. Well, we can think of that like maybe it's being tugged on one end and that's stretching it out. It's a little bit like that with these wavelengths of light. The wavelengths start pretty close together. Here's wavelength here. And they end up stretched out, which is like the galaxy moving away from us, pulling on that wavelength and stretching it out. And so that's how we can say that this galaxy is moving away from the Earth. And that answers our first part of this question. It's being redshifted or stretched out in wavelength. Now, the second question is, what's the speed of that galaxy relative to the Earth? Well, in order to find that, we have to turn to the Doppler equation. So this redshift of the galaxy moving away is sort of like a Doppler shift when it comes to sound and frequencies of sounds. Let me scroll down a bit here. We'll take a look at the Doppler equation, which you may have seen. F naught equal to Fs 1 plus V relative over C. So what this is the frequency at the observer is equal to the frequency of the source multiplied by 1 plus the relative velocity between observer and source divided by C. So if we go ahead and rearrange this equation a little bit, it's the relative velocity that we're trying to find. So the velocity between the galaxy and the Earth. So I'm going to start by distributing that Fs here. This gets multiplied by V over C. And then what I'll do next is just multiply both sides by C over here, F naught, multiplying that by C as well. So we get C F naught is equal to C Fs plus, and now the C's here cancel out, Fs be relative. Subtracting the CFS here over to the other side so that we get C F naught, or F observer, sorry, minus C F of source is equal to F of source times their relative velocity. I'm just going to factor out a C on the left side, and then lastly we'll divide by Fs on both sides. And so this equation here will be the relative velocity C times the difference an observed frequency and source frequency divided by the frequency of the source. At this point, we don't know the frequency, but we can figure that out using the wavelengths that we've been given. So if we think of F observer as being the frequency of the light found at the Earth, where the observers, then that's going to be equal to C divided by lambda of our observers, or lambda F is what we've been calling it. We'll keep that lambda F here. And then likewise, the frequency from the source, that is C divided by the wavelength from the source, our lambda initial that we had. Plugging those in, we'll get about 6.906 times 10 to the 14th. And so that's just using lambda in terms of meters. So converting from nanometers, 1 nanometer is 10 to the minus 9 meters. And so we convert lambda into meters using C equals 2.9979 times 10 to the 8. That's the speed of light in a vacuum. You get a frequency of about 6.906 times 10 to the 14 hertz for the observed frequency, and then the frequency at the source, about 6.835 times 10 to the 14 hertz. Now we have frequencies that we can plug in to this equation down here for the relative velocity. We plug all of that stuff in, and you'll get something like 3.1 times 10 to the 6 meters per second. So this galaxy is moving away from us at this speed.